Hi, this is lecture 10 of agricultural electrification. We are now in distribution. We revert back to the figure 1 from the last lecture, and we now zoom in on the last leg of the delivery of electricity, that is distribution. The substation where the high voltage electricity is stepped down in voltage is operated by the distribution side or distributors. And in implementation, these are the cooperatives like Casureco and Aleco, but there are also firms or companies such as Meralco. Now, from the substation, conductor wires are delivered to utility users via suspended wires, or in some cases, such as in um, Bonifacio Global City, underground cables. In most parts of the country, um, wires hang over the utility poles. Underground cabling may be safer against typhoons, but it can also be risky during earthquakes. Now, with regards costs, the latter, or the underground cabling is generally costlier than suspended cables. All right, just to show you that we are now in the distribution side in this figure. Okay, back again to this illustration where we've shown that the electricity, okay, so we are now focused on this area, okay, from around 14,000 to okay 2,000 to 14,000 volts, okay. And we have the transformers, okay, so from the substations. These are the substations, okay. You have the substations here, okay, and you have the residential and commercial customers at the end of this line. So in the Philippines, the standard outlet voltage is 220. So it's 220 volts, and it's actually stepped down from around 250 to 750 kilovolts, okay, in the substations. And again, we have different utility providers, such as that of cooperatives such as Aleco or Pasoreco, and we have also corporations such as Meralco. Now, both are again utility service providers of electricity and operate under the franchises granted by the Congress of the Philippines. Now, electricity prices are regulated by the Energy Regulation Commission, with the National Electrification Administration in charge of the technical and financial enhancements of these cooperatives, and particularly in the rural electrification. Okay. In cases of islands such as Catanduanes and Masbate, they have power barges, or floating barges, and these are providing electricity because they are not connected to the zone grid. The distributors, okay, so these distributors purchase power supply agreements, or PSAs, or they are involved in a spot market called Philippine Wholesale Electricity Spot market, or the Philippine WESM, okay, where they buy, okay, blocks of energy from power producers. Now, there are two main service systems for distribution, and we have the most common in the Philippines, which is the single phase system. Every household connected to the grid has an outlet of 220 volts of electricity. This is the most common, but other systems exist as needed. We have the 225 or 250 volts, and you have the 600 volts. If you go to other countries, they have different standards, and it depends on the country of implementation. The single phase originates from the step-down transformer, and the schematic of the 220 volt single phase system in the Philippines is shown in Figure 3. Recall the transformer diagram from the last lecture, and presented is the same setup, but with the addition of neutral and two hot wires. And both of the hot wires are 120 volts different to the, I mean, they are different, there's a difference of 120 volts between the neutral and the two hot wires. Essentially, the neutral is grounded the same way the neutral of the primary winding is grounded. Okay, if you could see, it's grounded. And this is where now ground wires of electrical appliances should be connected, because it's really an important connection. Unfortunately, most service outlets in the Philippines do not make use of the ground or neutral connection to the utility. This is actually very important in terms of safety. Okay, and we'll be covering that in the next lecture after this one. Also with overcurrent protective devices, okay, something like that. Now, the 250 volt Philippine single phase system is somewhat similar to the 120 slash 240 volt single phase system of the United States. And this is shown in waveform and phasor form in the figure shown on the screen right now, Figure 4. In place of the RMS voltages of 120 and 240 are the Philippine voltages of 110 and 220. Another thing of concern why these diagrams are shown is because the Philippines does not make use of the 110 half voltage, so representative of the hot to neutral connection. In phasor form, the degree of separation is clearly shown to be 180 degrees. If you have then a device connected, or a device you bought from the United States that's rated 110 volts, and you plug it to a 220 volt what do you call this outlet in the Philippines, it may burn, it may explode, or it may burn the overcurrent protection device inside. The waveforms are not in phase, okay, in this diagram, but are in sync to result in an RMS voltage of 240 volts. I think we have already discussed this in the last lectures, probably 5 lectures ago. Now, the three phase, and it's actually generated by an alternator having 3 identical armature coils spaced 120 degrees apart. Recall again the phasor and waveform. So this coil, okay, these 2 coils are spaced to 120 degrees apart, and also for this one, Likewise, this one. Now, this induces, this is connected to a load, okay, via this connection, and likewise this other one. And this is the whole load of the, for example, an electric motor in a shop. Now you have different connections. For example, this is the phase current, okay? This is the phase voltage. Again, remember your junction rule. You have in junctions, you have the current, okay, distributed, okay, it's distributed between two elements in the wiring, but in the voltage you have the same. No, I mean, sorry, in junction rule you have the voltage breaking up, okay, because this three are parallel to get to each other. Now the IL, okay, you have the oh, sorry, yeah, so you have the I got confused myself. So you have the current, okay, dividing when it's parallel to each other. So the IL now is different from this one, okay, unlike if it's in series, okay. So the voltage distributes itself or breaks down to component elements based on the ratings, okay, of the resistance. But in parallel settings, you have the current distributing among the elements. So you have the IL not equal to IP, but the ELL equal to the phase voltage, okay? Okay, you have it here. Now the IL, if you compute that based on the 120 degrees difference, you have it as 3 raised to 1.5, or the square root of 3 times IP. So that is the relationship if you are using a delta connection. For a Y connection, on the other hand, okay, well, let's just briefly go through this one. These are setups of the three-phase connection, where you have a single phase output from the from a 240 volt, okay. Oh no, this is actually, yes, this is a you have three phases here. So you have 240 volt phases, but the actual output here, it could be computed, it's just not computed that, but you have a three-phase output here, okay, from 3 points. And you just are using the 240 volt one phase. Now the problem with this situation is you have to have a balance of the use of all the phases. So you have phase A, so you have the phase A, you have phase B, and phase C. You have to balance the load among these phases if you're going to make use of the single phase from a three-phase connection. So if it would be, I think, much better to make, if you're going to consider using a single phase, then just connect separately to the main line or to the service entrance. Now the three-phase Y is something like this. It's letter Y in view. Okay, if you look at it. Now there's a difference now with regards the computation of the line-to-line voltage, while the line current is equal to the it's equal to the phase current. Why? Because they are in series. Okay, so this is in series going to the one element of the load. Now uh, the phase voltage now has a relationship to the line voltage via this equation. You compute the line voltage as 3 raised to the 0.5, or it's just the square root of 3 times the phase voltage. And this is now a graph of, or the waveform of that load. So you have phase A, okay, phase B, you have phase C. And what can you see here? Okay, you see that unlike in a single phase voltage, you just one have. So if you recall that you can make use of one phase in uh, a three-phase voltage, so remove phase B and remove phase C. What you see is one waveform, and that has a high and a low. So you have an RMS that is lower. So when you have a three-phase, you have actually a more efficient power delivery system. But the problem now is that you have more components, more circuitry, and that would be more costly than a single phase connection if you were just using two lines to distribute your electricity or power. Now, in the next lecture, we're going to talk about the uh, safety of using electrical systems, or yeah, with our activities. And electricity should be of great value to study safety. I will see you by then, and thank you for listening.